For today's lecture, we are going to be talking about capacitors and capacitance. So let's start by introducing what a capacitor is. So the overwhelming majority of capacitors that we can buy from Mauser, DigiKey, or whatever our favorite electronics purveyor is going to look something akin to this, or at least it's generally based on this particular concept. So I'm going to put a plate here. This is some sort of conductive material. Could be like a thin film of metal, or some sort of plastic that's been doped very heavily so that it makes it conductive. And I'm going to have a second plate underneath, like so. Okay. I'm going to attach an electrical lead to this plate, which I am going to very creatively call the top plate. And I'm going to attach a lead to this bottom plate, which I am, again, very creatively going to call the bottom plate. And this configuration is what is commonly referred to as a parallel plate capacitor. Okay. So in between those two plates, there may or may not be what's called a dielectric medium. So we can think of it as there always being some dielectric medium, but sometimes that dielectric medium is literally a vacuum or the absence of anything. And that dielectric material will have some sort of material properties. So I'm going to draw this in pink, like so. And I'm going to try to just fill this in. So this is our dielectric material between our plates. And the properties of that dielectric material are going to change the capacitance that is exhibited by this system. Okay. So I want to talk a little bit about how a capacitor works. Okay. So essentially, if I were to apply a voltage across the terminals of this capacitor, plus minus V, like so. The positive polarity terminal of my applied voltage is going to wind up attracting electrons from that top plate, okay? And so as those electrons move towards that positive polarity terminal of the voltage source, I'm going to start to accumulate some charge, which I'm going to call Q plus, on the top plate. And very similarly, the the negative polarity terminal on that bottom electrode of the applied voltage source is going to essentially repel electrons or force them to try to accumulate on the bottom plate. So we'll have some stored charge Q minus on the bottom plate. Okay. And whatever amount of charge we have stored on the top plate will be identical to the amount of negative charge we have stored on the bottom plate, because this thing is going to be electrically neutral. Okay. So what's really interesting about this, and you guys probably intuitively know this if you haven't really thought about it. So for those of you that have taken Physics 202 for sure, you are aware that positive charges repel each other and negative charges attract each other, okay? So how that plays into what's going on here is effectively the first positive charge I put on my plate, on that top plate, goes on there very easily. But every subsequent positive charge I try to put on that top plate is a little bit harder to put on there because those positive charges are repelling each other. So effectively, it takes me performing work in order to get those positive charges to accumulate on that top plate and those negative charges to accumulate on that bottom plate. So since it's taking work for me to put those charges there, this is a form of energy storage. If I supply some amount of input energy to the system, it holds those charges there. And then as soon as I lower that voltage, it's going to release those stored charges back into the circuit, okay? So that's the energy storage mechanism for a capacitor. It's storing all of that energy effectively in the form of an electric field. So whenever we have accumulated charge that is separated by some distance, what we'll see is that we'll have electric field lines that are oriented from the positive charge to the negative charge, like so. So we have an energy storage mechanism similar to that of the inductor, meaning that we have energy stored here in the presence of an electric field, whereas in the inductor, it was the energy stored due to the presence of a magnetic field. But the mechanism by which the energy stored is very, very different. Okay. So these are the basics of how essentially capacitors work, okay? We essentially store energy on the plates in the form of charge and introducing that electric field. And then as soon as we change that voltage, some amount of charge is going to be released back into the system, okay? So from that relationship, we could say that the current that's flowing through our capacitor, IC of t, is going to be equal to the derivative of the charge stored by the capacitor. This is literally just our fundamental definition for current from our second day of class. And we can relate this to capacitance and voltage because capacitance is just the constant of proportionality effectively between charge and voltage. So this will look like C dV by dt. So this is our first equation. Now, before we go into this guy anymore, I want to introduce you guys to the schematic diagram representation of capacitors because we're going to see two of them, okay? And a lot of people use them interchangeably, but that is technically in error. There is an actual difference between these two symbols, and I want to talk a little bit about that here in just a moment, okay? So the first schematic symbol that we might see is something like this. It's literally just representing two parallel plates because, as I mentioned earlier, the overwhelming majority of capacitors are indeed some form of a parallel plate capacitor, okay? So we would indicate the size of the capacitor by its capacitance C, okay? I can say that the voltage drop across the capacitor is VC of t like so, and the current flowing into the capacitor is IC of t like so. And I've indicated that the current is flowing into the positive polarity terminal for absorbed power so that capacitors are going to obey the passive sign convention like every other thing we're dealing with in this class, okay? So this is our schematic symbol for a generic or non-polarized capacitor. And for what it's worth, all of the capacitors that we are going to deal with in this class physically in our labs and stuff like that are going to be examples of these non-polarized capacitors. Okay. Our other symbol that we might see is this guy. So I'm going to have one parallel plate, and I'm going to have what looks like a curved plate on the other side, okay, where once again, I'm going to denote the capacitance of the device as C, the voltage drop across the capacitance as VC, and the current flowing through the capacitance as IC. This symbol is what is used for electrolytic or polarized capacitors. So in an electrolytic capacitor, if we were to apply the wrong polarity of voltage to it, the capacitor would actually burst. Okay. So a chemical reaction occurs that releases a bunch of excess gas, and it causes the capacitor to literally burst. I'll show you guys a picture of one here in a moment so that we can see how that bursting happens safely. Electrolytic capacitors are used predominantly in a lot of power electronic applications where essentially there should never be a negative voltage in your system. And so this is a way to indicate whether or not your device has been damaged. If you see a capacitor having burst, then you know that somehow a stray negative voltage occurred due to a short or some sort of other type of electrical incident. And the capacitor burst essentially to protect what's going on. So I want to pull up a quick, just literally just going to open up Google here and search for electrolytic capacitor and pull up a picture. Let's see if we can find a better one. Those are fine. This is a good one. All right. So this is an example of an electrolytic capacitor. You guys, if you've ever opened up the power supply for your computer or anything like that, or any type of electronics device, you've probably seen something like this. This stripe here with a very large minus signs on it is telling you that's the negative polarity terminal of this capacitor. It also has printed on it that it's got a capacitance of 3,300 microfarads, and we'll define what that unit of microfarads here is in a moment. But what I really want to bring your attention to is this plate on top. Notice that it has these score lines across it. Those score lines are to allow that top to mechanically deform to relieve some of the pressure when this guy bursts because it was connected improperly or saw a negative voltage across it when it should have only seen positive voltages. So there's something physical on here that we can literally see to indicate that this capacitor has gone bad. That will essentially dome over because those scores make that diaphragm effectively very easy for it to deflect. Okay. So this is an example of an electrolytic capacitor. It's still a parallel plate capacitor, but usually it's two parallel plates that are kind of wound around each other like a cylinder. Okay. A non-polarized capacitor most of the ones that we see in this class are going to look something like this guy here in orange. The ones in your kits literally look like those guys up there. So it's literally just two plates, two flat plates sandwiched next to each other. There's a dielectric material and then they encapsulate it in plastic so nobody gets shocked, kind of thing. So no polarization, no electrolytic material that's going to burst or anything like that. Doesn't matter how we connect them, they are going to exhibit some level of capacitance. So we use non-polarized capacitors in this class because it would be far too expensive to use polarized capacitors because you guys don't pay enough damn attention and you might hook up something backwards and waste nickels and dimes at a time as you blow shit up. So I'm cheap, so I used non-polarized capacitors for the labs here. Okay. All right. So just wanted to show you a couple of examples of this. So let's talk about our units here. And we can sort things out by looking at this first equation. So I'm going to rewrite this because we're going to look at it again. So we've come up with the relationship that IC is equal to C times the derivative of the voltage with respect to time. And I said this was equation 1, and I'm going to put a box around it because it is important. Okay. If we look at the units, I have current obviously measured in amperes on the left-hand side of my equal sign. I have capacitance that I'm trying to figure out what the units for that are. And then I have the derivative of the voltage with respect to time. So that's going to be something in volts per seconds. So it seems like the units for the capacitance is going to be in amp seconds per volt, so that the volt cancels, the second cancels, and I'm left with just amps on both sides of the equation. We are going to call that amp second per volt a farad, where 1 farad is 1 amp second per volt, which is the same thing as a Siemens second, or because capital S multiplied by S is a little bit hard to see, we might have it as a per ohm times a second, or seconds per ohm if you prefer. Okay. So that is the unit of capacitance. All right, so circling back around to the equation that I boxed in here, equation 1. I hope that this looks vaguely familiar to you all. So what I mean by that very specifically is it looks a lot like the voltage relationship for an inductor, right? So the voltage drop across an inductor was V is equal to L di by dt. So we have that same basic form, except that we've swapped current and voltage, and we've replaced inductance with capacitance here. We are going to see that that is true for every single one of the relationships today. Every equation that we get for our capacitors is going to look exactly like the equations that we got for our inductors, except that we swap I and V and we replace L with C. That's because capacitors and inductors are what are known as electrical duals of each other. They perform the exact same role, but they use the opposite mechanism. Capacitors deal with electric fields, inductors deal with magnetic fields. And so we're going to see that that relationship propagates through literally everything that we do, okay? So let's look at this relationship here and see if we can infer something about the behavior of capacitors in our circuits containing capacitors, like we did with circuits containing, goodness gracious, circuits containing inductors on Wednesday, okay? So if I have a DC system where all of my voltages are constant, what would we expect the current flowing through any capacitors in that circuit to be? 0, because the derivative of a constant voltage is 0, okay? So if all of our capacitors are going to have exactly 0 amps of current flowing through them, what do they behave like in a DC circuit? An open circuit, which is the opposite of a short circuit that inductors behave like, right? So I can say that in a DC circuit, IC of T must be 0 amps, and then capacitors behave like an open circuit. So for the next relationship that we can glean from this guy, we could do a series of examples like we did with inductors, but we can also just figure it out because we know that inductors are going to behave in the opposite way of capacitors. So the second relationship that we got from our derivative-based relationship for inductors was that the current flowing through an inductor could not change abruptly. In doing so, it would generate infinitely large voltage spikes, right? We talked about that. Well, in a capacitor, we'll find that the voltage drop across the capacitor cannot change abruptly, because if it does, it generates infinitely large amounts of current. Okay. So I'm not going to bother with the derivation for that, because we've already seen that exact behavior when we were talking about inductors on Wednesday. Okay. Excuse me. So mathematically, I'm going to represent this as VC at T approaching from the left must be identical to VC at T approaching from the right. So once again, in this case, the voltage drop across the capacitor has to be a continuous function of time with no discontinuities or anything like that from a mathematical perspective. Okay. So pretty darn similarly to what we did on Wednesday, I could mathematically rearrange that relationship for current in terms of voltage, and I would find that my voltage drop across my capacitor, VC of t, could be expressed in terms of my current as 1 over IC times the integral from negative infinity to t of IC of t prime dt prime, which is the same as 1 over c times the integral from t naught to t of IC of t prime dt prime plus VC at some time t naught. And this is our second relationship. Again, exactly identical to what we saw with inductors, except that we've swapped I and V and replaced L with C. The power absorbed by a capacitor will be the product of capacitor voltage and capacitor current. And we can replace our capacitor current in this case with equation 1, giving us the relationship that we would have C times, the capacitor voltage multiplied by the derivative of the capacitor voltage with respect to time. So this is equation 3. And following an extremely similar derivation to what we did on Wednesday with inductors, we could say that the energy stored by a capacitor is going to be the integral from negative infinity to t of Pc of t dt. And this is just going to come out to be 1/2 times the capacitance times the voltage drop across the capacitance squared. So I've now introduced our 4 different equations that govern how capacitors behave in circuits. And I cannot emphasize this enough. They are the exact same relationships that we derived on Wednesday for inductors, just swapping I and V and replacing L with C. Okay. So the last thing that I want to officially talk about in this lecture then is how capacitors combine in a circuit. Okay. So let's say that I have a system containing multiple capacitors in series. So here's some capacitance C1, C2, all the way out to C sub n, like so. Let's say that the voltage drop across this combination of capacitors is going to be some total voltage V of t, and the current flowing through this string of series connected capacitors is going to be, let's just call it I of t, sorry. And I'm going to label my individual capacitor voltages as V1, V2, and so on all the way down to Vn, like so. If I were to apply Kirchhoff's voltage law around this loop, I would find that my total voltage, V of t, is equal to the sum of V1 plus V2 all the way out to V sub n. I could use my second equation that we developed to express all of those voltages in terms of my current. And so that would look like 1 over C1 times the integral from negative infinity to t of I of t prime dt prime plus 1 over C2 times the integral from negative infinity to t of I of t prime dt prime all the way out to 1 over C sub n times the integral from negative infinity to t of I of t prime dt prime. And I can see that I have a common factor of that integral, right? So essentially, I will have a factor of 1 over C1 plus 1 over C2 all the way out to 1 over C sub n times the integral from negative infinity to t of I of t prime dt prime, or 1 over CEQ, the integral from negative infinity to t I of t prime dt prime, where CEQ is simply 1 over C1 plus 1 over C2 all the way out to 1 over C sub n, and I take the reciprocal of that sum, or in summation notation, that's going to look like 1 over the sum from I is equal to 1 to n of 1 over C sub I. So essentially, capacitors in series combine like resistors in parallel. So they even combine opposite the way that we would expect as compared to inductors. Okay. So without doing math, how do you guys think capacitors in parallel are going to combine? Like resistors in series. All right, so that is officially where I want our lecture on this material to end. Same point that we effectively ended our lecture with regards to inductors. Much like I did at the end of Wednesday's class meeting, I want to look at some of those web work problems from this homework set because there are a few that can be rather tricky, okay? So if I pull up web work assignment 12, we look at problem 1 here. This is a fairly straightforward thing. And you've got an in-class assignment problem that is extraordinarily similar to this. That's problem number 1. This is just exploring the different mathematical relationships governing how a capacitor behaves. Nothing wild or crazy there. If we look at problem number 2, we have an inductor combination problem and then a capacitor combination problem. Nothing particularly wild or crazy there. It's literally the exact same network. It's just they're going to combine opposite because one's inductors and one's capacitors. So nothing super crazy there. If we look at problem 3, this is where things start to get a little wonky, okay? So in this particular problem, we have a single loop circuit where we have a voltage source in series with an inductor in series with a capacitor. So the only thing we have are energy storage elements, okay? So I believe I discussed this a little bit on Wednesday, but whenever we have a circuit like this where everything is connected in series, what should our first step be? Kirchhoff's voltage law, okay? So ultimately here, in this particular problem, we are simply trying to find the voltage drop across our source, and that will be the voltage drop across our inductor plus the voltage drop across our capacitor. So let's take a look at this guy and how we might try to solve it, okay? So we've got a voltage source here, Vs of t, that is ultimately what we are trying to solve for. I have some inductance here, L. Everybody's value, I think, is going to be different. And then I have some capacitance here, C. And the capacitance, Vc of t, is a known quantity. So Vc of t is known. Vs of t is what we're ultimately trying to solve for. Okay? So what I would do in a situation like this is I would define the voltage drop across my inductor, VL of t, like so. And then I could say, using Kirchhoff's voltage law, that Vs of t, the thing that we're ultimately interested in finding, is just VL of t plus Vc of t. Since Vc of t is known, the only thing we really have to figure out here is what VL of t is, and then we just add those two together, right? So does anybody have any thoughts on how we might find VL of t in this problem? The current, exactly right. So the same current is going to be flowing through both of these elements, right? So if I define this current right here, and I'll do it in blue, as I of t, I could say that I of t is simply going to be C times dVc by dt. And so from this, VL of t is going to be L times di of t by dt. Substituting in I of t, this is going to look like L times C times the second derivative of our capacitor voltage with respect to time. And then coming back to the beginning, then we'll have LC times the second derivative of our capacitor voltage with respect to time, plus just our capacitor voltage with respect to time is the source voltage that we're looking for. So not particularly hard if you know what you're doing, but most of you guys probably aren't used to essentially setting up second order differential equations. So giving you guys a very strong starting off point for this problem. Anybody have any questions about the process that I used here to just set things up, and I'll leave you to do the grunt work of the actual math. All right. Oh, Brendan. How did I get the LC? Because I took the derivative of I, and I is the first derivative of V. So taking the derivative of the derivative is the second derivative. Yeah. Any other questions on this guy? All right. So let's go back to the web work really quickly. Let's look at problem 4. I don't remember it being much of a pain in the ass. So we're just given a graph and we need to figure out the current flowing through the capacitor, the power absorbed by the capacitor, and the energy stored by the capacitor. So I think you guys had something very similar to this in homework set number 11. And if I'm remembering correctly, I think problem 2 from the ICA is something pretty similar to this as well. So nothing wild or crazy here. And then we get to problem 5, which you guys tend to think, and I'm not in total disagreement, is the hardest homework problem that you will face in this class. It looks deceptively simple, but it does take a pretty good understanding of what all of the relationships that we've dealt with, or at least the current and voltage relationships for capacitors and inductors are, so that we can apply them to this system. It is a time varying source, but anytime we're dealing with capacitors and inductors, we should expect time varying sources. I would consider, so like it's not an AC, I don't want to get on too much of a tangent here, but when most people talk about AC sources, they're talking about sinusoidally varying sources, like the voltage that's supplied by the receptacles and stuff in our classroom. Our source in this case is an exponentially decaying source. So it is changing in time, but it isn't what most people would classically think of as an AC source. So I want to take a look at this guy to give you guys some very strong hints as well. Okay. So I'm going to modify it slightly. We've got some source voltage Vs of t, which if memory serves me correctly is a known quantity. I have some equivalent inductance, which I'm just going to call L. So I'll leave it to you guys. Actually, let me look at that real quick. It was the capacitor there, but it doesn't matter. I'll just draw it the same way though. So some equivalent capacitance, excuse me, C. And then over here on the right, I have some inductance L. And my ultimate goal in this particular circuit is to find this source current Is of t. So I'm given the following information. Vs of t is a known quantity. Is specifically at t is equal to 0 is a known quantity. And my ultimate goal is to solve for Is of t for t greater than 0. So because this is a single node pair circuit where everything is connected in parallel, my first step is going to be applying Kirchhoff's current law, okay? In order to apply Kirchhoff's current law, I'm going to need to assign a current to my capacitor and my inductor, right? So let's say that this guy right here is IC of t, and this guy right here is IL of t. So I can say that IS of t is simply going to be equal to IC of t plus IL of t. I don't know what either IC of t is or IL of t is, so now I'm going to have to use those current voltage relationships for capacitors and inductors to sort that stuff out. So let's start with the capacitor, right? So IC of t from equation 1 that we learned today is simply C times the derivative of the voltage drop across the capacitor. And since everything is in parallel here, the voltage drop across the capacitor is just our source voltage, right? So that's going to look like C times the derivative of Vs with respect to time. So nothing wild or crazy here. We should all be able to take the derivative of an exponential function. So IC is the easy part. Carter, what's up? Okay. IL is going to be a little bit harder to sort out. Okay. So we know the voltage drop across our inductor. We're trying to find our inductor current. So that is equation 2 from Wednesday, the integral-based relationship, right? So that's going to look like 1 over L times the integral from some time where our current is known to some later point in time of Vs t prime dt prime plus IL at time t naught, where our inductor current is a known quantity. And so herein lies the trickiest part of this whole problem. We weren't given the inductor current at any point in time. So it's a little bit hard to figure out what we should use for our initial condition. Okay. So while we weren't given that current specifically, we were given enough information to essentially find it. Okay. So if Kirchhoff's current law, IC is equal to, excuse me, IS is equal to IC plus IL, has to be valid for all points in time, then it has to be valid at t is equal to 0 as well, okay? So essentially, I could say that IS at 0 is equal to IC at 0 plus IL at 0. And rearranging this, that tells me that IL at 0 is just IS at 0 minus IC at 0. So that's just IS at 0, which is a known thing, and then minus C dVs by dt evaluated at t is equal to 0. So essentially, if we find what IC is, we just plug in t is equal to 0, and that gives us our IC at 0. Now that we know what IL at 0 minus, or excuse me, at 0 is, we can plug that into our integral expression for IL, and then we can fully define what our inductor current is for all time. And then we simply add those results together. So it is genuinely a tricky problem. I have set up, I would say, 85-ish% of the problem for you. I'll leave you guys to bring it home, but if you have any questions about it, obviously, you're welcome to ask. That's the last problem on the homework set. It is, like I said, a difficult one. For what it is worth, and you'll see this in some of the practice tests and stuff like that, I do like homework 12 problem 3 and homework 12 problem 5. So something like this may very well show up on exam 2. But it would probably be the very last question on the test, meant to be the most difficult problem on the test, kind of thing. So just giving you a heads up. These two homework problems are stuff that I like, so expect to see something like that on your exam. But I do recognize that they are genuinely difficult. So that's the quote unquote alligator problem type of thing that you'll see on exam 2. Okay, any other questions, comments, or anything like that for me? Yes. This is number 5 from homework set number 12. And then the previous problem that we worked at was homework set, problem 3.